a lot of hot air. Now this is actually a friend of mine and also Dave Glacken's. Dave's friend first, David Glacken, who was a member here and his sister donated all the money for your equipment. Paul Steinhardt, he was actually roommates with Dave Glacken when they were at Caltech, and so they knew each other real well. And I found out that, of course, oh yeah, I'm hot to meet Paul Steinhardt and get him to come talk at Embry-Riddle at my annual Elston Memorial Lecture on Gravitation, which actually meets now at the same time as the Astronomy. We have famous people. I had Nobel laureates there, Alan Guth there, all kinds of people there. Some of you probably heard of Kip Thorne. He kicked it all off. He's been on TV. He's been in the movies. And he was the one who headed the Gravity Wave project for many, many years. Anyway, Paul's a really nice fellow, stand-up guy. And also, this is Alan Guth, and were discoverers of inflationary model and solved all these technical problems that people were worried about. So they're very famous. There's also another guy, Andre Linda, and I couldn't find a good picture of him, so I didn't know him. Anyway, these two have a little beef there. And last time I talked to Paul, he was in town, of course, he was in an Elston lecture about 2 years ago. We're sitting in Panera's down there on International Speedway. Oh, you don't know that because I'm in the wrong city. Okay, well, scratch that. But you know about Panera's. And I'm asking about this controversy. He was saying, well, some people think now this is new physics. You have millions of possibilities, and you pick the one that works. Okay, and Paul says that's not science. And I've seen him give speeches to, a whole body of other cosmologists, and he says, we got to get real here. We are not actually understanding things. We're getting models that kind of give us what we want, but we have to pick the right one out of an infinite number. And that's not science. Science is you try to understand why something happens, you understand what it is, etc. You don't just say, oh, let's take that one because it matches. It's kind of like, oh, there's X, I'll circle it. So we agree on this point, and I feel good about agreeing with such a great man. So, all right, now this is why it's so hokey. And now we got equations. And some of you are probably equation savvy, but this is almost like visual. It's more than anything else. This is an equation that's telling us about the energy density of the universe. Well, we got some energy density right here. We've got a lot of it. We could turn it in. E equals mc squared. We turn it into a blow up the whole city, just with that little piece there, and counting maybe. All right, and well, this is like kinetic energy of motion of a certain kind for a scalar field, and this field is a function. Okay, and we don't know what that function is, and this is a v, a function of a function. It's called a potential. Okay, but these are mathematical quantities. Now, this is my question to Alan Guth. He's just given his talk. He stayed at my house. They're on the way to the airport, and I said to him, just as I said earlier, I've been studying your theory, and I just don't know where the inflaton comes from. He says, just like that, he goes, that's the only thing we have to figure out. It's like, that's the only thing we have to figure out. And oh, okay, yeah, it's like the whole theory, right? I mean, you don't have anything. Is that what you're telling me? I didn't say that. I'm more polite. Okay, it took me 10 years after my PhD to realize I went to Avi Ashtakar's talk, a great man, and he invented the, let's see, what was it? Well, that was too technical, but the loop theory of quantum gravity. Okay, and it was kind of a cool idea, but it didn't go anywhere. And after 10 years of watching him speak, I'm sitting there in Canada, and I'm watching him speak, and I'm thinking to myself, I thought I was just confused all this time. These guys knew so much more than me. I would never be able to, take a long time to understand them. I'm looking at his face, and he finishes his talk, and I'm thinking, he has no idea what he's talking about. He's as clueless as I am. Well, not quite, but he's still clueless. And these are hard problems. It's not easy. It's not easy. Anybody in these areas could have the right idea. They kind of degenerate into cliques, so you have to go along with the flow of one idea, or you don't get anywhere. You don't get grants, you don't get tenure, you don't get this, you don't get that, which is regrettable. A friend of mine, Lee Smolin, you might have read some of his books. He's written some great books on the universe. Okay, he wrote a book called The Trouble with Physics, and he described this completely, and it is a big problem. You have to kind of get in with the gang, because the gang controls the grants. They'll control the entries into the journals. They will not take your papers. They got plenty of friends that they need who agree with them that they're going to publish first before they publish anything from you. Okay, and you would think these are scientists. They're men and women of great character. They're selflessly spending all their time doing science. No, they're human beings just like you and me.
Could you be quiet?
Oh, sure. I'd be happy to. In fact, Lee, for writing that book in an article in Physics Today, I said he was going to give a talk, and I said, Lee, why don't you tell us about this controversy? It's very interesting. He was a string theorist, and he studied string theory. For a long time, he published papers. He was internationally known for string theory, and they said, please come to our conference and tell us all about string theory since it's our original idea. He went to the original idea, and he said, wait a minute, something doesn't seem right here. He called up the author, and he says, does your paper mean to say this? And the author says, no, it never meant that. And all of string theory was based on that one paper and a misunderstanding of his paper. And I said, you're sure? He says, I'm absolutely sure people understood they don't understand my paper. It's not true. Okay, and he published that, and he says, this is the problem. We are stuck in groupthink. Anybody ever feel that way? Yeah, sure. We're stuck in groupthink, and we are not allowing people to express themselves freely. You know, it's not scientific. Okay, so that sets in anywhere. It's true here, it's true in any group of human beings, because we are imperfect. We want to be correct. Yeah, it'd be great if we were correct. But you know, these are very tough questions, and it's really not bad to be wrong. Lee Smolin said, actually Shirley reminded me of this, Lee Smolin said that string theory is not even wrong. It's not even wrong. That's a quote from Lee Smolin. String theory is so deficient, in other words, it's not even wrong. Somebody would say, oh, here it is. It's not even wrong. Well, it doesn't say anything. Will it say anything? Okay, and it has not been verified now. So these are little functions, and where did they get them? There's a little bin over here, and they pulled them out of the bin, and they stuck them there. Oh, that one didn't work, I'm going to throw it back. Well, let me fish around here. I'll find another one, and I'll put it in. Do you think I'm kidding? I was interested in giving this talk, so I didn't know too much about dark energy, so I asked a friend of mine who's in relativity also, and at Embry-Riddle. You know any good books? And I knew he worked in cosmology on dark energy, because I want to read up some. He sent me the book. He said, yeah, this book is good, so I bought it. Sight unseen. I said, oh, well, this is great. It's going to be wonderful. I opened up for 2 or 3 pages, and this is what I was seeing. I knew that was from somewhere else, and I was hoping they were doing with the inflaton, but I was hoping they were going to do better with dark energy. The dark energy and the inflaton depend on making up functions. Now, why is that so bad? You don't know where they came from. You don't know why this is the one. It's not an equation you're solving. It's like x is here, circle x. Oh, this one worked. It worked at circle x. This must be the universe. What is it? Is it a proton? Is it a neutron? Is it this or is it that? Is it an object or a thing? It's just this funny looking thing with sines and cosines and exponentials and this and that. And I stuck it in there, and it seemed to do something for my theory. Question?
So what you're saying, dark energy and dark matter still leaves us in the dark.
But we don't know what they are yet. Well, I'm going to tell you I'm going to tell you a little bit more. Okay. See, Shirley told me that everybody wanted to find out what dark energy and dark matter was, and I was thinking, oh, well, that's a big order. So, I know I can't do it, but I can tell you a little bit about it. So anyway, so this is really just for your benefit. You don't need to understand these equations. You need to understand they make something up to stick in there. Okay. What works? Let's make something up. That's not how normal physics works. Okay. Any more than something X. All right. So now we're on to dark energy. Very short bit of dark energy. I wanted because it's really not very different from dark matter. They use similar artifices. The expansion of the universe is accelerating because dark energy, unknown material exhibiting repulsive gravity. We see that Einstein can deliver repulsive gravity if we have the right kind of matter in there. Negative pressure does it too. It doesn't have to be a rubber band. Thank goodness, it wouldn't work, right? But you can create situations where negative pressure develops. If there's negative pressure, it will create repulsive gravity. Do they have evidence of this? Well, it's all in the early universe. And it's happening now. So it must be out there somewhere. It's happening one way or another. You know, and people will say, oh, it must be coming from the false vacuum. Now, you say, what's a false vacuum? It has technically, you get small enough, and there's going to be a zone where particles are created and destroyed automatically right here in this room. There's like submicroscopic. Have they got evidence for that? Yeah, you can put 2 plates together, and you're going to be very, very close together. And then something called the Casimir effect. It will be actually attraction from one plate to the other. It's not electromagnetic, but it's due to the initiation and the creation and destruction of particles that you can't even see happening. But they've measured. Very, very tiny. Very, very tiny. Could it be some kind of artifact. Well, it's been repeated, so something's happening. Okay, and it matches the theory. So, all right, then we have a new theory of gravity changes. So that's one cause, a new material. The other is maybe gravity works differently on a large scale. Maybe it works differently, period. Okay, that's more back into mathematics. Okay, Einstein thought of his equation based on curvature. We talked about, oh yeah, go around, take the vector around, it can curve. But if that's not the case, it'll be dark. But his theory might be wrong. See, there might be some adjustment we can make, and we'll get the right results. Now, he actually had a cosmological constant, he called it, the biggest blunder, Einstein's biggest blunder. He said the biggest mistake of my life, and it predicted dark energy type rapid expansion of the universe in like 1920. About 1920. See, so this has been known for a long time, except back in those days, I mean, there was a couple big blunders. For one thing, they didn't know about the expanding universe. He thought the stars were just sitting up there. Everybody thought they'd been there and kind of in the same location in galaxies, and so the galaxies were thought to be wisps of gas. They were not systems of stars. They were just, some gaseous nebula. They called them nebula for that reason. They were just nebulous little gas here and there in nice patterns. Okay, so they knew nothing of this, so he actually introduced the cosmological constant to make the universe, to give a repulsive force that would keep the universe from imploding. Newton always worried about that. Isaac, he said, well, you know, we got the whole galaxy. Why aren't they all, my force of gravity attracted, why have they not come all together and destroyed themselves in one giant black hole or whatever? Well, that's just not going to happen. Because, and he said, well, the cosmological constant might do it for us, but you can use the same cosmological constant to predict dark energy type expansion. So, you know, it's actually his greatest success. You never know, you know, well, some people are just more lucky. So, okay, dark matter. I can't tell you what's in the dark matter sandwich. No one knows what's in the dark matter sandwich. Now you know as much as I know about dark matter. Okay, so, why dark matter? Stars in our galaxy are moving too fast. Okay, they should leave and never return. And that would not be helpful. We would be leaving with them. Okay. We'd still live with it. Our son would go with us and we'd be okay. But we'd be stuck out in, you know, the suburbs there between Andromeda and our galaxy or somewhere. Okay, there must therefore be matter embedded in the galaxy we can't see, which is dark matter. Now, Fritz Zwicky came up with this in 1936. He kind of noticed this going on, and but he didn't pursue it too much. He was famous for all kinds of funny faces. Philip Penko had that great slide. What was it? He was making some referee or something made a report he didn't like, and he called him a spherical bastard. A bastard no matter what direction you looked at him from. A very salty guy. Then we have another possibility. Physics works different on a galactic scale. Now, we have little problems with this, you know, as well. So we'll take a look at the observations. Now, the galactic rotation curves, here they are. Now, we've got velocity up here. We've got distance from the center of the galaxy. That's in thousands of light years. And, you know, look, 10, 20, 30. We know that the galaxy is about 100,000 light years across. Okay. And we see that the actual data points that go up here. Now, this dotted line, this is how they should go. Well, that's a disconnect, right? Now, that means, basically, you've got to travel on this dotted line. If you don't travel on the dotted line, well, if you were down here somewhere, you would fall in the center of the galaxy and be destroyed by the giant black holes there. If you are up here, you should be flung away from the galaxy and be lost in intergalactic space. But that obviously has not happened. So, so they say there must be some more matter that is hidden in the galaxy and keeping these stars from traveling away from the center, even though they're going too fast. Okay? So it's pretty simple. This has been known for a long time. There's a lady named Vera Rubin. You've probably read about her, maybe, maybe not. And she measured the velocities of lots and lots of different stars, and she really put this on a very firm foundation. Now, that's which galaxy? I think that's our galaxy. Well, they're very similar. That looks like ours. Let's go to the next one. Now, here's the rotation curves of other galaxies. Now, look how different they are. Look how different they are. So, I guess we could say, some of them almost look like they're normal. See, this one here, it goes up like so, and then comes down like so. You know, that's, well, whichever, I can't read it from here. And they're obviously all very different. I've seen actually more detailed maps. I couldn't find that image. I had it on my computer somewhere. and it was showing some actual more raw photographs, superposed over raw photos, a whole bunch of them, and they were really crazy looking. They were crazy looking. All kind of more or less the same general shape, but you know, something like the thermal spectrum of a hot object, you can say, well, which wavelengths are present and how many? It looks like this. Okay, you cool it down, it looks like this. You make it hotter, it looks like this. They all look the same, the shapes look the same. It even looks like the microwave background shape, like this, okay? So, why do we have all these different ones for something like this? Well, you say, well, the Odysseys look different, they're irregular, they're this, they're that, they're spirals, elliptical, and so the dark matter must not be distributed the same way in every galaxy. Okay, I can accept that, I guess, but you can see this is not going to be easy to figure out with all those differences, and we don't even know where the matter is in the other galaxies. So, okay, now these are the explanations. Newton's gravity force law becomes stronger at greater distance, and here's his force law. See, there's a mass, there's a constant, an r squared. So it's a 1 over r squared force law. If you're twice as far away, it's 1/4 as strong. Okay. So pretty straightforward. Now, here's another possibility. Newton's F equals ma, that's the second law of motion. That means F is a force. You put a force on something, it's got a mass. The bigger the mass, the harder it is to push, right? But then you have an acceleration. So bigger the force, the more the acceleration you're going to get, okay, for a given mass. So very simple laws that have always been used for the entire galaxy, but now don't seem to be working anymore. So maybe that's the problem. Maybe that's the problem, wrong force law at big distances. Maybe that's the problem. Somehow Newton's second law stops working, sorry. An unknown type of matter provides initial gravitational attraction. We talked about that. That's probably more likely, I would say. Some combination of a new force law, new dynamics, and or unknown type of material. So you can combine all three. You see how hard this is? This is much harder than inflaton or dark energy. So we thought our chances were shaky with the inflaton of dark energy. Now it's even worse with dark matter, in my opinion. If I wanted to solve one problem or the other, I'd say, well, let's leave that for dessert. We'll never get there. Okay, so a guy in Israel, what is his name? Something like moliform. Sounded like something you could drink in order to settle your stomach. But I forget right. Maybe oh, here it is. Milgram. Yeah, Milgram sounds like you can drink it in your stomach and feel better. I remember people going around and talking about this at dinky little conferences 30 years ago, and probably Milgram was there. You know, it probably was him. I was sitting there not knowing he was going to be famous. And he smiled and looked at his compatriot and he said, well, we know the answer to that. And then he gave this entire thing. So, okay. Yeah, well, I don't think I believe you yet. Anyway, so Milgram had this law of motion. It's pretty funky. So you can see it kind of looks the same. There's a mass. There's this is very important. You got a little A naught there. You have to choose that A naught yourself. Okay, it's a number. It's a number. And it will actually does the following thing for you. I'll show you in a minute. And then here's the law of gravity again. I just put it there for review. And you can use these little things, do a little algebra. And then if your acceleration is much less than A naught, and it gets smaller and smaller as you go out in the galaxy, because then we get the following. We get that the velocities should be constant. So that's what they see. So you go out of the galaxy, they're supposed to go down like this, but instead they go up, 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 and then they start to flatten out and become constant. And it actually works pretty well for a lot of galaxies. Okay, so it's not totally without merit. So we can ignore those. Yeah. See, I told you I wasn't going to show you too many equations. We got some bad stuff coming up, but it's really more like looking at a Matisse or Picasso or
why isn't modified Newtonian gravity well accepted by academia? It seems that dark energy with some sort of matter. I mean, you can't really be sure that gravity is acting exactly the same throughout the entire universe.
Well,
you know,
right.
it seems more logical to me that the gravity is somehow different there than here, and that's causing the effect. But there's no way to measure it, right?
Right. Well, no, they're measuring the effects, and they are getting pretty good numbers. This is not a failed theory by any means.
Oh, it's not?
It's not failed yet.
Oh.
It's not popular, and I was at a dark matter summer school at SLAC. That's the linear accelerator in Stanford 2 years ago. And there were a lot of people there that thought it was just junk, and a few that really liked it. I'm one of the ones I kind of like it because I'm pretty sure that Einstein's theory is not correct. You know, it can't be. Okay, so there's something, what you find when a theory is incorrect, you find that there's things happening that you can't explain with the theory. The theory is incorrect, period. It's incorrect. Now, it might not be incorrect in every way. You try to make an improvement. That's what real science is about. And, well, I don't know if you're into climate science, but there are plenty of problems with climate science. This is not a climate science lecture, but one word, entropy. And any scientist should be able to take that word and apply it to climate science and realize we're in big problems here. We're having big problems on every level with the whole concept of not only what is happening, what we can predict, but also if we can affect what we predict. Well, the problem is we can't predict, so we don't know what to do about it if it goes bad. Just, oh, what a crazy subject. I'll come back and talk about that next year if anybody wants to. Oh, it took me 10 years. I had to study this stuff, because, I'm writing that book, and I'm working on the new revisions. We got a couple sections on it. Okay, I got to keep up to date, so I read all these papers, and I kind of keep up with it. And the first movie I saw was about Al Gore. I just took it at face value. Okay, you must be right. It's in the movies. So then I started to read up on this stuff in the background. It's kind of like Lee Smolin in his aha moment when he realized, wait a minute, the fundamental assumptions are wrong. And there's some of that going on in climate change, and people don't like to hear that. Even if you're not really dissing it, you're just saying there are deep mathematical problems with prediction of what's going to happen. You can predict it in the past if you're lucky. Future? Forget it. Not in your chaotic system, you're not going to predict the future. What's going to happen is you're going to make a prediction, and after the future happens, you're going to say, I was right, or wrong. And it's hard to design a mitigation for that, and then entropy says you can't design any way, shape, or form, mitigate what's happening. You cannot control the thermodynamics of a bottle of ideal gas. You can even put a cork in it. So how are you going to do it for an entire planetary atmosphere? And the answer is entropy keeps you from doing it in a flask. Now, go out there, you got non-ideal gas, you got an entire planetary atmosphere. All your refrigerators to cool off, it's not going to work. Okay, entropy. That has not sunk into the consciousness.
But CO2 is increasing in the atmosphere.
Yeah.
Oh, yeah.
Okay, that's all it's based on.
Yeah, that's all
it's based on.
There's about 20 different
There's
major
no other
effects.
argument except the increase in
There's
CO2.
about 20 different major effects.
But CO2 is increasing, and most of it is from human activity.
Well, that's true, but you see, you notice you only mentioned one thing. There's about 20 other effects. That could be causing it. CO2 might not be doing it. Okay, so it took me 10 years. So I don't want to get into that lecture because we'd be lecturing for a long time. But it's not that it's wrong, it's complicated. And see, my position on it is they need a lot more research and study. And they need to have trial projects in one small location and see if they can make it work.
But the system is changing at a massive rate, and we are dumping more and more CO2. I mean,
we're dumping a lot of other things
what
too.
we inherited is massively changing on a global scale, and we're
not
dumping.
as massive as you think. It's been steady for about 20 years now.
No, but as far as the overall environment, it has.
Oh yeah.
The forests are disappearing. There's more asphalt, and there's more CO2. So
For 1 cent.
whether it has it has a predictive effect, theoretically you can't predict anything.
I'm agreeing with you.
Gentlemen, can we bring this back to the...
Yeah. See, I'll tell you.
He brought it up.
So, science is complicated, and people sometimes don't think deeply enough about these problems. I'll tell you afterwards. I'm not disagreeing with you at all. Everything you said, I agree with. That's not the point, but I'll tell you afterwards. Okay, we got the Andromeda Galaxy, and here it is. And one of the problems with dark matter and the MONS system, modified Newtonian dynamics, is, well, here's the Mon point right here. Where the heck is the Mon point? and this was actually Michael Turner. He was used to be a few years ago, he was the head of the Office of Science and Technology in D.C. and the National Science Foundation. And he used to tease the MOND supporters and Milgram about this. Where the heck do you put the MOND point? That's when you choose that one number, A0. And the thing is, you don't know. So what you do is you have to change it to make it work. Here's X, circle. It's not quite that bad, actually. It's actually better. So this is an almost successful theory. Now, the problem is, it's probably not going to work. That's the mathematical end of things. And very hard to prove one way or another. It has a lot of good things. Some people argue about some bad things that it doesn't predict properly. All very technical. Here are some possible sources. Neutrinos with mass. Everybody know what neutrinos are?
Yeah.
Okay, you probably heard of them at least. But they're very, very hard to detect. They can go through light years of lead. Strangely enough, you can actually make beams of them now and fire them at targets. You can detect them with baby oil, okay, but you need about 1 million tons of baby oil in a line, deep mine. Okay, and then they look for, the neutrinos will go through the baby oil, they interact with the baby oil, and they'll create some products. It's not just straight baby oil, it's mostly baby oil. They'll react and they'll create some traces of certain products in the plant. Okay, so maybe they have, neutrinos have mass. Now there's another guy I know, that Daryl Smith, and he was working with teams, and there was theories out, and they predicted that some neutrinos have mass, and so probably, that's a possibility, there's enough of them to create the dark matter. Not certain. All right. And it's not, or even their masses are not certain either, still. WIMPs, weakly interacting massive particles. What is a WIMP? Well, nobody knows. But they have gigantic experiments going to try to detect oddball particles that they have not seen before. Over at CERN in Switzerland, they've got a giant ring, and they create particles every day, different energies, and they're looking for WIMPs. Things that, oh, who ordered that? Where did that come from? What the devil is that thing? Okay. Can you imagine they spend like hundreds of millions of dollars and they can't find anything? What are they doing with all of their money? I'll show you in a minute. Axions, low mass, low, they don't interact, there's no charge. Theoretically, they think, what is an axion? I couldn't even tell you, but it's another one of these WIMPs. Okay, a lot of WIMPs out there. Macho! Finally, we got somebody with some hair on their chest. Now, what does that stand for? That stands for Massive Astrophysical Compact Halo Object. White dwarfs, brown dwarfs, and neutron stars. And you're all familiar with those. Okay, so brown dwarfs, well, that's something about, 50 times the size of, not the size, the mass of Jupiter, about the same size as Jupiter. We have a lot of those. I actually kind of like that. I think that's very, very likely. We've got a lot of those out there we can't detect, except maybe in the infrared. Yeah.
Would stellar mass black holes be included amongst machos?
Oh, sure, sure. It's hard to see those too.
Yeah.
So,
We
well, I didn't put that there.
detected a few with LIGO.
I didn't put that there. But I would say that you could put, I should have put it in. If I didn't put it in, if nobody else put it in, they should have.
Yeah.
Because they're hard to detect as well. You know, all kinds of smaller black holes. There might be micro black holes. There are micro black holes left over from the beginning of the universe. And they might be out there. And they're very tiny but very massive. Okay, and let's hope they don't run into us. So then they have a Kaluza climb. This is associated with the fifth dimension. I'm not into fifth dimensions. We have the Gravitino, partner of the graviton. That's a very technical particle. They haven't seen any of those. And, well, actually, I have a theory myself because I'm developing a unified field theory. And you know about electric charge? You stick a needle on. Well, don't do it, but in a socket. Okay, so we got electric charge. And I did that once before, but 4 years old. It was fun, but I didn't want to do it again. I flew across the room 10 feet and banged into the glass door. And just recently, I was thinking about it. I was thinking, how could I have jumped that far? And I didn't do it on purpose. You know, the electricity helped me, I guess. And I found out the world record for a man jumping backwards is like 6 feet 7 inches, and I went about 10. And I thought, this is great. I'm the world record holder. I need to advise someone to change the record book. Okay, and they'd probably say I cheated because I used an external source of energy. Okay, so, all right, so maybe a new course. So you can see I can't really tell you what it is. I can tell you what it might be. These neutrinos, well, there are millions of neutrinos streaming through your body right now from the sun. The sun makes these like gangbusters all the time because they come from nuclear reactions. And there's lots of nuclear reactions in the sun. So there's hundreds of millions, billions probably going through this room, just like we're the ghosts. You know, it's going right through like we're not here.
Like right now.
Right now, this instant. In fact, every instant of every day. You cannot even make a shelter against these things. To them, the entire Earth is like an open window. That's not an exaggeration. It's very hard. You know how long they have to wait? They have these big tubs of baby oil. Not tubs. They're not tubs. They're like entire mines full of it. They got to wait years to get reactions. Finally, we got one. But see, they got a lot of nuclei there, right? There's a lot of different atoms. So, all right. So let's see. Oh yeah. So here's our particle zoo. So you can see there's lots and lots of different particles. We could spend weeks on particles. Here's the an experiment, very expensive experiment over in Switzerland or France or whatever you want to call it. I think that CERN straddles 3 or 4 countries, Italy one of them. And this is actually a gigantic detector, so you'd be some kind of small person who's standing there. A giant detector. And they create particles in that detector, and they try to create different new particles that are at different energies. Who actually looks at these runs? They do these runs constantly, like every day.
Computers.
All day long, 24/7, unless they have to calibrate or stop the machine. Nobody looks at them. Okay, why not? Nobody could ever look at that many different, pieces of data. They write computer programs that go through all the data and pick out the interesting ones and bring it to the human's attention. Now, there's a pretty big black hole you could drive through with that, right? What if they missed some really interesting stuff? Well, because they didn't know what to tell the computer to look for. You never know. So it's something that they can find so much with that kind of constraint. Okay, so and here's what's happening. They have basically the detector looks like that in cross section, and all the reactions and the particles are in here, and they're trying to get out. And so you can see the photons trying. Let's see, is that a photon? Yeah. That's a particle of light. It gets stopped in this area, and you've got an electron. It'll go through here and to a certain point and stop. You've got muons. Remember a muon. Well, that's a very fast electron, and it's denser, so it has more momentum. It's getting almost all the way out. It's getting out of the detector here. Then we got protons. They get trapped in this area here, and you got neutrons getting trapped over there. So they basically can find out, and these are all detected, so they can find out what the different particles are that are reacting. So a reaction happens, and then the particles fly off. They know what the particles are. How do they tell? And this does it. This is doing the same thing as that, except linearly. You can see, oh yeah, stopping there, going all the way through. This is how they identify the particles in the reaction. Now, what does that have to do with dark matter particles? Well, the dark matter particles we're not seeing. Look, there's a little missing energy. That's what ET means. Missing transverse energy. And we add up all their different momenta and energies. Because they penetrated through these different shields to different distances, you can tell how energetic they were. You can calculate that. So you can say, wait a minute, we're missing some energy. And of course, momentum counts too, even more so really, in certain respects, because it tells you the direction. And that energy should be right along here. There should be a dark matter particle traveling along this line, if it's just one of them. Okay, it has to travel along that line, or else something is missing, because energy is not created or destroyed, right? You have the reaction, you know what the total energy should be, and it's missing. So when they see that's missing there, they calculate, okay, what is this? This is evidence for an invisible particle that we can't detect. Okay, so that's how they're trying to find it. And it's kind of I went to that meeting, they had all these giant graphs, and they said, we have ruled it out here, we have ruled it out there, and it was all colored, different colors, and they're trying to make it smaller and smaller. And I guess if they cover up the last spaces, then they'll say, well, wait a minute, I guess we just better start over. I don't know. So this is just a sort of a diagram. See, if it looks like this, we're okay. See, you run them out particles at each other, they bash together, and then some go this way, some go that way. But notice you got some going that way, some going that way, some energy going that way, or momentum going that way. It all balances out. You say, this actually then is equivalent to that in terms of momentum conservation. But you see the red one, maybe the red thing is missing. Then what you see is you say, oh wait, the particles are going that way, but there are no particles going that way. So we're missing something. Something invisible is going that way. Okay? That's how it works. All right, and here is what it looks like. It's like, what, 27 miles around or something. Humongous. Been there for a long time. CERN is these are different experiments. And I keep forgetting their names. That's why they give them short names, cute names like Alice, Atlas. And I don't know how they mess those up. They don't seem to say anything right. All right, and these are all their names. Large Hadron Collider, Compact Muon, Solenoid Particle Detector, a Large Ion Collider Experiment. Yeah, I was really interested to find out how with Alice and Atlas, of course. So these names actually do mean something. Okay, now the other experiment is a xenon experiment. And here they got liquid xenon. Searches for WIMPs with 3,500 kilograms of xenon. Particle interaction, liquid xenon creates tiny flashes of light, and they analyze the light and say what kind of particles we have, what happened. Do we have a WIMP? Okay, and here is oh look, somebody put a toy dollhouse over here. I don't know why they put that in the picture. Oh wait a minute, that's not a toy dollhouse. That's an actual building. Not the first floor, the second floor, and the third floor. And I don't know what they do. They sit around and play cards there, I guess. But over here, we've got a giant tank of water, and the xenon is inside there. And notice that it's 3 stories tall, right? These things are all gigantic and big. But where is the actual detector? It's inside, and here it is. This is the WIMP detector that has the actual liquid xenon in it. Xenon is a noble gas, very heavy noble gas. And so he is a technician inside the big blue building there, big blue tank.
And isn't that big blue building like 1.5 miles underground in the mine too?
Oh, it probably is. I forget how deep they are, but
Yeah.
it's underground and has to be. You have cosmic rays and other junk come down, and that's why they do these things in the bottoms of mines. Is because then you shield out cosmic rays traveling from the center of the galaxy at the speed of almost the speed of light, and it'll plow through a lot of matter, but it can't reach you at the bottom of the mine and cause spurious readings. Okay, and here's the secondary WIMP detector. Okay, the 3 biggest questions in science: what is inflation, dark energy, and dark matter? We want to find a theory for each one, or one theory that explains them all. And we're running out of time here, so I'm going to. Quantum gravity may be the key, and that's another thing people haven't figured out. How does the physics of the very small, which is quantized into, you've seen this TV show, okay?
Quantum leap.
And you have quantum jumps. I just tried to do a quantum jump, I failed. But little particles can do quantum jumps, and they can do funny things like they can. In fact, if it weren't for quantum jumps, the sun would not shine. You don't know that? Some of you probably knew that. Did you know that? What happens is you've got a couple of protons coming toward each other, and they're both the same charge, positive charge. They're so powerfully charged, electromagnetic forces are very strong, and they repel. And there's no way this particle could ever hit at those temperatures, ever hit even in the center of the sun and fuse together. There's no way they could do it. Okay, but fortunately, there's quantum mechanics, and they come to the barrier, and the barrier is stronger and stronger, and then they go through anyway. And every single bit of energy we get from the sun is because quantum tunneling, and this quantum jump through a barrier exists and works. Otherwise, we wouldn't be here, obviously, we wouldn't be here. So it actually is, quantum mechanics is real, it does happen, it's been verified. So has gravity and the gravity experiments. Remember, gravitation, general relativity, the most accurate theory in all of physics. And their theories are, at this point, we notice that this equation is beautifully simplified if we assume that space-time has 92 dimensions. Well, believe it or not, I talked to a guy once, and his theory had like 500 dimensions, okay? I said, oh, that's interesting. He says, oh, yeah. Trust me. I didn't trust him. Okay, so we've got to go back to the blackboard. This is how we got E equals MC A squared. No, it doesn't work. P squared. No, that doesn't seem to have quite the right. He's almost there. Now, unification is like relativity in quantum theory is like a round hole in a square peg. And in 1987, I had an idea for doing this. And I'm just going to go straight to the picture. I wanted to make a bridge. And here's general relativity in quantum theory. And I was going to create a probabilistic theory of gravity based on probability, like rolling the dice. God does not play dice, but we're not going to go with that anymore. You heard that saying before? God does not play dice. This is what he was talking about. No, quantum mechanics, it stinks. That's what he was saying. Quantum mechanics stinks because of this reason, this reason, lots of reasons actually. You could say it stinks, but we're not going to do that anymore because we have to play dice. All right, so I was going to create a theory that used probability instead of curvature of space-time. I was going to get it to satisfy all the different solar system experiments, all those great experiments of the pulsars going around each other. And then, once I had that theory, I thought, well, quantum theory is very probabilistic. I will see the right way forward. Okay, it hasn't happened yet. Okay, so that was in 1987, I said. But I was walking across the street like this, bingo! And the idea came. Here's the idea. And if this ever works, it'll be a miracle. This is the simplest theory currently in physics. Nobody knows about it except me, really. I presented at conferences here and there. And the last one was pretty good. There was 15 different groups presenting. I was a group of one. And they were all doing stuff from Vuille's theory of gravity from 1920. I was thinking, oh, that's an old idea, man. Mine was the only different idea, and I'll show you exactly what it is. Very simple idea. I'm going to get from point A to point B. And I can go the blue route or the red route, and we'll say there's a probability associated with each point along that path. What if I just add those probabilities up from here to there? and add those from there to there. And what if I get a big number for the blue path and a small number for the red path? When I add up those probabilities, which path is the particle going on? The blue path, right?
Yeah.
If I add up and the probabilities at each point, being at each point, are kind of a big number, and I go along here, it's a small number, you think, well, this is the more probable path that's going to go along that path. Now, amazingly, what I realized crossing the street was that this was actually a condition I could apply all this really high-powered mathematics to pick out the path that you were going on. Okay, there's something called, Newton invented on a night of indigestion. And it is so powerful that engineers and scientists have been using it ever since. And it solved problems, for example, what shape does a chain fall into when it's under gravity? And I could use that theory to create my theory. So that's a very simple picture. Any child can understand that. Anybody can understand that. Okay, yeah, this path is more probable, it's going to go along that way. There's a mathematical tool now called the calculus of variations that Newton invented, and I can tell you what path it's going to follow. I can actually do a calculation based on just this idea. Okay, and okay, this is what resulted. This is where we're looking at the abstract art here. But this first equation you see here has all these gammas in it. You see, and those all came into the equation. It's supposed to be equal to 0. I don't know why I left that off. This is actually an acceleration. These are all kinds of forces and fields, and one of them is pseudo-Newtonian. One of them is electromagnetic. One of them is a gravity force. So they were all in there, and I was shocked when that happened. It didn't happen right away. It happened after about 20 years. Then you have to find out what those fields are, and so I calculated this at least 200 times. Every time I'm in the doctor's office, calculate. It takes about 10 pages. You make one mistake, everything is wrong. And it was wrong at least 200 times. And I was on the plane in 2011, and I was calculating again, and I found that I had a piece like this. This is exactly the same as general relativity in vacuum. I had a piece like this, exactly the same as electromagnetism in vacuum. And I had a piece like this, which is actually the same as a quantum field equation in vacuum. And it all came from the little picture. So it's the simplest theory in physics. Now, simple is good if it works. Okay, so I had all the tools. And here's Einstein's space-time in 2 dimensions. Here's Kaluza-Klein, which is 3. Here's mine. It's in 2 dimensions, but it's got, oh, that's funny. It's got something stuck over there. That's actually a quantum dimension, so to speak. Okay, that's the quantum dimension. So in this theory, the higher dimensional theories, you can actually travel in these other dimensions, theoretically. I don't have any extra dimensions in my theory. You can't travel there. Okay, but it is an extra feature. And it's the quantum feature. And if you're really into mathematical, there's something called the space of smooth nonlinear differential operators. That's like the big cloud. In the cloud, we have these polynomial tensors, and they're dense in that cloud, which is a technical term. And I'm using actually a really small part right here. It's called the subalgebra of the cloud. That's all I need to get what I need to get. And this is what everybody else is using over here. That's very old style. Multi-linear. Notice there's only one of those at a time. See, one here, one there. They're not added together. Mine are added with these things called direct sums, which, by the way, you've been doing direct sums ever since you were in grade school. Okay. Even physicists don't realize they're doing it. Okay. I know. Why did I know? Because I took all these hours of abstract math when I was too foolish to realize I should be in physics instead of math. It's weird. I learned a lot of useless sounding stuff, but almost nothing in math is useless. So I like to characterize my theory like this. It's a bizarre hybrid. We've got, this is the standard physics like general relativity. This is quantum theory, and you just stick them together, and that's kind of how my theory looks. And it's even worse when you try to visualize it. I confess, I got a little, here's one of my cosmologies I calculated. I have an inflaton region, I have a flat space region. 5 billion years later, boom, dark energy inflation. So I can actually get a model of dark energy out of my theory. And, but there's a lot more to do than that. You think, oh, yes, you won. Now, like I was telling you, science is complicated. So no matter how good it looks, no matter how convinced you are you're right, you're not right. Almost certainly not right. Very difficult to get something right. You have to have some shocking good luck and some shocking good agreement with experiment. Some of the old ones, like Bohr's theory of the atom, got a Nobel Prize for that. He had nice discrete little values, something like climate science or even something like cosmology. It's very, very messy. You're talking about decades working on something and hoping you're going the right direction. But people don't appreciate that because they're not in science and they haven't done this kind of stuff. It took me 10 years to appreciate it. You know, after my PhD, I started saying, this stuff is really hard. What made me think I could be a physicist? Isn't it time to second guess my major again? There are a lot of easier ways of living. Now, I don't think we have enough time to keep going. Or if you just want to escape, you could. This is fairly short, time. And I wanted to tell you a little bit about time, because it tells you a lot about the universe. And about time is absolute and immutable. And unfortunately, it's not consistent with electromagnetism. So our usual concept of time, click, 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 is not right. Okay? It seems right, and in most speeds it's right. Now, in studying time, measurements of time depend on the relative velocities of observers. Okay? So if you're moving your clock, your watch runs slow relative to somebody else. But then you say, well, wait a minute. From my point of view, they're moving, and that's a giant paradox. Why isn't their clock running slow too? And the resolution of that paradox is very, very difficult. I won't do that tonight. Okay, and it's not even easy, not even clear that it's been, you know, Einstein's theory of special relativity works perfectly, and it has for dozens of decades, but still there are simple little things like that that people don't understand. I'm talking about physicists like me don't understand well enough to explain it. It's not that it's so deep that you can't understand it. It's so deep that nobody can understand it. And that reminds me of Eddington. I was going to tell you. He said, somebody asked him, is it true you're that only 3 people in the world understand general relativity? A reporter asked him that after his mission. And he says, who is the other one? And that's unfortunately, that's really true. Feynman, have anybody heard of Richard Feynman?
Oh, yeah.
Sure. Great guy. I never met him, but great guy. I was saying I read a lot of his work. And he had a good sense of humor and everything. But he once said, I don't think anybody in the course of history has more than 12 people have understood relativity. He says, on the other hand, nobody's ever understood quantum mechanics. And this guy got a Nobel Prize for just that. Physics is hard. Do something else. All right. Now, that's the Einsteinian move. So if you're moving fast, your clock runs slow. I'll run around the building. They've tested this with clocks in airplanes, atomic clocks, compared to the clock left behind. Oh, sure enough, it's short a few nanoseconds after you float around the world on a pan am. Okay, so absolutely true. Now, we're going to go to Fomalhaut, which is a big star, bright star, 25 light years away. And here's we got, what's her name? I forget.
Natalie Portman.
Well, wherever it is. Doesn't matter. Here's Einstein. They leave the Earth. And they come back. Oh, look at that. Okay. Einstein is the old one, and she's still young and beautiful. Okay, and he's old and hairy. So, and see, I'm old, but I'm not here, which I'm very happy about. So, all right. So in Einsteinian general relativity, it's a little bit different. Time depends on your position in a gravity field and how much gravity you are feeling. Now, you can have be on a mountaintop, or you can be here. Where do you think has the higher gravity? On a mountaintop or here? Here, because we're close to the center of the Earth. Okay, so typically you can have a lot of differences. Now, these are actually very important to everyday life, and they're important for. But anyway, a clock in a strong gravity field runs slower than clocks in weak gravity. So it'll actually run slower. They've tested this from a distance of about, I don't know, probably just a few meters, but with lasers and something called the horsepower effect. And they can test this theory exactly. So it is true. It's simply true. Of course, this is used, of course, in astronomy, good distances, yeah.
I've read that Einstein's equations were originally not covariant and would not have worked with the first Crimean solar eclipse. What does that mean exactly, covariance?
He changed his mind many times, and that's another lecture. But yeah, he changed his equations many times. In his first formulation, there were technical problems. I'll tell you afterwards. It's pretty technical. It's pretty technical.
Well, what's a basic layman's explanation?
What's the basis? Well, what happened was he found the one that worked. And that's the one he went with.
Okay.
And the other ones he crossed out. You can actually get a Dover paperback and you're reading. I got one. I said, oh, here's some of his early papers. I want to read them. Huh? What's he thinking? Well, everybody forgot about that one. Okay, it didn't work. Okay, so we've got the physical passage of time depends on your position. In strong gravity, your clock runs slower. All right, so here we are at Gargantua. You have to go someplace with strong gravity so we can get this effect down. And another nice picture. That was a great movie. Kip Thorne consulted that movie for several years, and he talked to me a little bit about it. Here's a problem with falling toward a black hole, a real problem, and that is that your top of your head is pulled not as much as your feet, and you'll be stretched out like you're on the rack until you die. Okay, and it won't take long, unless you've got a very, very heavy black hole, and then you can last longer. Okay, so it's also the lines of the tidal forces are coming like that. Just think of a ball, and the lines of gravity all go to the center, right? Well, when you're near a black hole, those lines going to the center like that are actually squeezing you too, and that's why they call it the spaghetti problem. They turn you into a piece of spaghetti. Ouch. Ouch. Okay, so that can be easily calculated by somebody in virtual physics. Okay, can tell them what to do. Okay, so we're going to take a trip to Gargantua. I'm not going to tell you who went, and you're going to tell me at the end who came back. Who actually went on the trip and came back. Okay, whoever it is, they're falling toward the black hole, approaching Gargantua in their spacesuit in free fall. They come back. Which one went to Gargantua? Okay, let's do that again. Okay, so start both young. And,
Einstein did.
No.
which one? How many people vote for the woman? Raise your hand. How many people vote for Einstein? Raise your hand. Okay, well, actually it's the woman, because she fell toward Gargantua and her time went slower,
Oh,
see, because the gravity field was higher, and when she got, and time ran faster for him. Remember on Interstellar?
Yep.
And they went down for an hour to the planet, and they came back, and 27 years had passed.
Yeah.
that's right.
Remember that? This guy says, where have you been? I've been in sleep. I wake up, I calculate for 10 years, and I go back to sleep. I get bored. And, oh, we were only there for an hour and a half. Oh, yeah, 27 minutes. And that's a deeper in the gravity field, and so up here, time doesn't travel as fast. Well, that actually turns out to be all bogus. I did the calculation. That was for Hollywood. There was no way, if that really happened, the people who went down to the planet are all dead. Okay? They're all dead. They never went down. They never came back. Okay? So it was just a fantasy. It wasn't just a small fantasy. It was as fantastic as saying, I can dive through the earth to the other side and come back in 5 seconds. I can't do that. Okay? That's how wrong it was. But otherwise, you wouldn't have any fun in the film, right? That's some fun in the film. So most of the effects were sort of real, but they were sort of imaginary too, for effect. And, oops, bad trip. Okay, so the endurance is up here. It's just the whole scale is all wrong. There's no way they could just go from orbit down to the planet. They would all be dead, in fact. They'd all be dead. Guy in orbit would be dead too. Okay, so warp space-time can allow faster than light travel. Wormholes through space imply possible wormholes through time. Now, nobody's sure that they've seen one of these yet. No, here's Kip Thorne. This is pretty much what he looks like. Here's a better picture of him. He's actually drawing the equations for the movie on the blackboard. So those are all authentic equations. And, well, there were some technical funny things that they talked about. It was a lot of fun watching, of course, for me to watch it. But he's an amazing fellow. Well, we don't have time. I'll tell you more about him next time. And so if you got an apple and a worm, you can have a hole. You can go right through the worm can go right through the apple, or you can be space-time. You see, you can go through the wormhole. And here's some fanciful little. Now, wormholes through space are like wormholes through time. So you could go through time as well, right? Space-time. Like Minkowski said, they're just the same thing. So here's a nicer picture. If we want to go from here light years away, we can go through the wormhole. It actually takes a huge amount of energy to do that. Interstellar wormhole. Okay. Problems traveling by wormhole, energy shortage, you need, Kip Thorne calculated you need a large fraction of the energy of the galaxy to make a wormhole. Okay, it's not going to happen, most likely, unless we just don't understand it. Narrow throat problem. Wormholes would be very narrow, perhaps allowing one object the size of a hydrogen atom at a time. We would have to disintegrate somebody. We assemble them in the Lego land problem. Okay, we got you through to the other side, now we got to put you back together again, because we can only send you through one atom at a time. Disintegration hazard, if any of your atoms touch the walls, Hawking calculated, you would be destroyed in a burst of radiation. Okay, doesn't sound very pleasant or possible. Time travel, there are problems with time travel. You get stuck in the deep past. I call this the die before you're born problem. ACA T-Rex hors d'oeuvres problem. Go to the past and convince mom that dad is a jerk. never-born problem. Now, then we got the go to yesterday 1 million times, unstoppable army of clones problem. Okay, see all these problems? I got my own problems, you see, here they are. Flatness problem, all that smooth problem. Forget that, these are real problems. Get future stock info and find you didn't go quite far enough, future financial self-con problem. All right, so this is pretty fanciful, the idea of traveling in time, but Kip Thorne actually spent about 10 years trying to figure out how to do it, he and all of the students. Very interesting. I saw that meeting like 30 years ago, and I put up my crazy theory, and it's not that crazy. It's working out very well, but I said, what are you working on these days? He says, he laughs a little bit, and he says, embarrassed. He says, kind of embarrassing, I'm working on time travel. Okay, well, somebody's got to do it. Oh, here's some nice little time travel. Artist time travel. Oh! Okay, we don't need to talk about that because we're almost out of time. These are interesting 2 dimensions of time that's been proposed. Parallel universes as other time dimensions. And we've got, the downside of time travel. We have, oh yeah, those are the warlocks, downside of time travel. But there's always an upside. And I actually have a whole bunch more stuff here, but I think I've probably taken too much of your time already. So, well, let me run to the end. Okay. Oh, this is a nice shot here. I calculated what you would see, and I looked for a picture on the web. This is pretty, you know those planets now, TRAPPIST planets? And they've got 7 Earth-sized planets. Well, one of them's more like, well, it's still pretty big. I calculated the gravity on the surfaces. It was always at least about 70% of Earth's gravity, so it'd be pretty comfortable living there. And if you look at the sky during the day, and they might not rotate, so it might be all the time, then you would see something 16 times as big as the sun. And this was a very good picture. That's about 16 times. You would see at least one object or two objects that are about the size of the moon. As you see there, there's one. And there's a smaller one. That would be C. I think C is a little bit smaller. Okay. So, and on the other end, at the night, there's 3 others that you might see. Now, you might see them here, too, if you're on the other side. So it's really interesting, and too bad it's, what, 45 light years away? I mean, that's a crying shame. And I could give you another lecture on trying to go there. And sorry, I was using this time to think about something useful. Okay, that happens to me a lot. And, oh, I like this one. This is one of the first talks I gave ever. It was to a huge audience. I put this up. I wasn't always a homeless vagrant. I'm a doctor, a research scientist. My specialty, may heaven help me, was general relativity. And that's all for tonight.
Thank you so much for coming out tonight.
Yeah, thank you for inviting me, Bob.
All right, thanks, everybody.
I'll hang around a few minutes if you want to chat some.
If you'd like to talk afterwards, stick around, otherwise